Hello, you are welcome to another lecture on the parabolic equations in 2D. Here, I want to give a simple illustration of the ADI method using a simple stencil. Okay. We want to just take a stencil where I runs from 0 to 6 and then J from 0 to 5. And basically what you want to compute using this approach, the ADI method, is to compute this red dots or the node. Yeah, you want a solution, you want U at the interior nodes, these guys. I especially want to demonstrate that it is important to alternate the direction in order to get a tridiagonal system or matrix. So that is basically why I want to illustrate this, why the method is called the alternating direction inverted method. All right. So I'll remind you of the procedure again. First, you compute this first step for U tilde. Once you have U tilde, you plug it in here and solve for your final solution. So in this lecture, I want to just concentrate on the first step. How do you get U tilde? Okay. So I'm going to expand this and then show that if you sweep in the horizontal direction, the resulting system is tridiagonal. So that's what I want to show. So I'm going to use the operators here to expand U tilde, the operator here to expand this. When you do that, you get this equation here. All right. I can pull delta x squared out, delta y squared out, and I can call this mu or alpha x, and then this I can call alpha y, and then rewrite this, and then you get an equation that looks like this. I mean, I can simplify this further by letting this term be some beta x, and then this term be some beta y, and then if I do that, I end up with equation 25. So the equation for the first step, solving for U tilde, is actually equation 25. All right. And so now you need to solve it for different values of I and j. And so the first step is to sweep in the horizontal direction. By sweeping in the horizontal direction, you take a value of j and then look for the resultant system for each value of I. All right. So that is what is referred to as the horizontal sweep or horizontal direction. Before I come to this, I'll just show you here. What this means is that when j is 1, I compute this for I. When I is 2, I compute for this one is 3, all the way to when I is equal to 5, and that gives me this. Okay, that is the horizontal sweep. After I'm done with the horizontal sweep, I move to the next level when j is 2, and then do another horizontal sweep, all the way to when j is 4. Okay, so that is called the horizontal sweep. So in the first step where I plug in n is 0 and j is 1, for various values of I for the horizontal sweep, I get the system of equation. Okay, now the right hand side here I just denoted by this red. It's just a notation to show that we know what is on the right hand side. These are known from the initial or previous iterations. So we know the right hand side. The stuff in blue, U tilde at 0, 1 and U tilde at 6, 1, these guys are actually the boundary values for U tilde. So these are the values here and the value there. Okay, those are the blue ones. Okay, so in the previous lecture we demonstrated about how you can get this. If the boundary conditions are not time dependent, are independent of time, then you can just replace this with value of U itself at the boundary, value of U at the boundary. So this will be known and that will be known, so you can take them to the right hand side, this one to the right hand side. And then the resultant equation, this is basically what I just explained previously. The resultant equations, when you take the boundary stuff to the right hand side and the other one to the right, is this. Okay. Now, this system, which is the same as system 1, we can put this system in a matrix form. All right. So if you rewrite the system of equations in a matrix form, then boom, this is what you get. The right hand side is given by this. You want to compute for this. These are the interior nodes, right? Just when j is 1 along the horizontal there for various values of I, these are interior nodes that you need to solve for. But this matrix here, that's most important, and it's now tridiagonal. And so you can use the Thomas algorithm to solve this. And again, the red ones are the right hand side, which are known. The blues are the horizontal, are the boundary values or boundary conditions, which you also know. So these are known. And so you can calculate this for the first horizontal level, and that gives you the solution of the interior nodes at that level. Okay. Of course, you can do that and move to the next level when j is 2 and sweep horizontally again. All right, for various values of I. And you get a system very similar to what we got for j is 1. All right. Again, these are the boundary values. 0, 2, and then 6, 2 are the boundary values, which are known. You take them to this side, and again you get the matrix equation, or a matrix which is tridiagonal, and therefore you can solve it. Okay. Now this is the same as I showed before. So you can continue. For j is 1, we just show that it is tridiagonal. You can move to when j is 2, do it for when j is 3, and finally for j is 4. And then that will give you the interior nodes for u tilde. Remember, this is just the first step. So you get u tilde for the interior nodes. Once you get those, then you can move to the next step and do another sweep. Now I will demonstrate that in the next step. Okay, in the next step, if you continue to do a horizontal sweep, the resulting matrices are not going to be tridiagonal. Okay, I will show that. And so it is important that in the next step, instead of doing a horizontal sweep, you do a vertical sweep. In other words, you take a value of I, let's say 1, and then get a system for different values of j, and then that will be tridiagonal. You compute it. Then you move to I and get a system for various values of j. All right, in that order until I equals 5. Okay. So at least for now, we've seen that if I do a horizontal sweep, the resultant system is tridiagonal. All right, which you can easily solve using the Thomas algorithm. Okay, so that is for the horizontal sweep, or if you like, the first step of the computation. Okay, in the next lecture, I'm going to show that in this next step, okay, it is important to do a vertical sweep. So I'll first show that if you continue with the horizontal sweep, you get a system that is not tridiagonal for this step. Okay, and then we'll move from there. So I'll do that in another video, another lecture. All right.